Imagine floating in the deep reaches of space and throwing a stone as hard as you can. Standard physics suggests it should fly at a constant speed forever, yet on a cosmic scale, that stone will eventually slow down and stop. Its energy does not transfer to anything else, it simply vanishes. This reality contradicts the basic lessons taught in every secondary school classroom regarding the law of conservation of energy. However, the explanation for this mystery lies not with Albert Einstein or Max Planck, but with a woman named Emmy Noether, a mathematician who was once denied a formal salary and even the right to stand at a university lectern. In the early 20th century, Noether changed the landscape of science by linking the physical world to the abstract beauty of mathematics. At the time, German universities systematically excluded women from academic life, forcing Noether to work as an unpaid lecturer under the names of her male colleagues. Despite these barriers, she produced a body of work that Einstein later described as the most significant creative mathematical genius since the beginning of higher education for women. Her primary contribution, now known as Noether's theorem, provides the underlying logic for why the universe behaves the way it does. The core of her discovery is the concept of symmetry. To a mathematician, symmetry means that something remains unchanged even after you perform an action upon it. Noether proved that every conservation law in physics is the direct result of a specific symmetry in the universe. She demonstrated that because the laws of physics are the same regardless of where you are, momentum must be conserved. Because the universe has no preferred direction for rotation, angular momentum is conserved. Most strikingly, she proved that energy is conserved only because the laws of physics remain constant over time. This insight reveals a startling truth about our cosmos. Because the universe is expanding, it is not the same today as it was billions of years ago. This lack of time symmetry on a cosmic scale means that, globally, energy is not actually conserved. When light travels across the void for billions of years, its waves are stretched by the expanding space, causing it to lose more than 99% of its original energy. This energy does not go anywhere, it simply ceases to exist because the symmetry that required its conservation has been broken. Noether's work did not stop at energy. Her second theorem solved a crisis in the theory of general relativity that had stumped Einstein himself. By distinguishing between global and local symmetries, she provided the mathematical framework that eventually allowed for the creation of the standard model of particle physics. This framework is so precise that it allows scientists to predict the existence of subatomic particles, such as the Higgs boson, decades before they are ever observed in a laboratory. Today, while her name remains absent from many introductory textbooks, Noether's fingerprints are on every major advancement in theoretical physics. She taught the world that the stability of our reality is a gift of symmetry. From the reliable operation of an engine to the steady replication of DNA, life itself is possible only because we inhabit a universe where physical laws are stable enough to allow complexity to grow. Emmy Noether did more than solve equations, she uncovered the secret architecture of existence, proving that even when a door is closed, a brilliant mind can still find the keys to the universe.